This is going to be the first lecture in talking about introducing you to finite element analysis. I want to talk about how I'm going to present this material to you. First of all, as engineers, it's not sufficient for you to just be able to plug and chug into existing software, especially with something that is genuinely as complicated and as powerful as finite element analysis or its partner in another type of computational solutions, which is finite difference analysis. So those two things are parallel partners. They're two different approaches. What you've heard of is FEA, finite element analysis. The way I'm going to present this, first of all, with this short video on just introducing you quickly to FEA, doing a simple example, showing it using both SolidWorks that you're familiar with now, which is why you're ready now to start looking at FEA. And we'll also do a quick demo with ANSYS, which is a more powerful FEA tool. Once we've done that in this first video, then I want to wind back and actually go through the equations with you, because it's really important that you understand the background. As engineers, you can't just plug and chug. So with that as the starting point, let's talk about finite element analysis. So the essentials. This is important to understand any of the tools that you'll use with FEA, and it will link back very fundamentally to the governing equations that I'll introduce later. First of all, you already know geometry in the sense that you can now create a very detailed, very accurate, very realistic 3D model using CAD. That's the essential starting point. So if you can't create a CAD model, then really you're kind of dead in the water with doing FEA. The CAD model needs to be accurate. So you're good at that now. You've been spending the past month and more learning how to do that. The next thing that every FEA solution needs to have in it are really accurate material properties. Again, you've studied this in some of your past courses, so you know about some of the basic material properties. In some of the analyses that you will do, there's some additional properties that maybe you're not that familiar with yet, but they're all powerfully represented in the equations that govern the model. An essential part, and probably the most difficult and important part for getting an accurate analysis, is the mesh. You take your 3D CAD model in whatever form you've made it, and you have to divide it up into finite elements. It's called finite element analysis for a reason, and that is because basically you're taking your 3D solid model and you're cutting it up into tiny little pieces. The shape, size, and properties of those pieces are what makes the simulation work or not. If you get the mesh or the division up into little pieces incorrect, then the model can't be trusted. The other important part, and we'll go through this with the governing equations, you've encountered this in math before: boundary conditions, initial conditions. Yes, fundamentally, what you're doing in finite element analysis is solving differential equations or integral equations. And the region over which the solution is valid is bounded by its surroundings. The starting point, the parameters at the boundaries are the boundary conditions. And just like the meshing, this is an essential part of creating a model. And if you get the boundary conditions wrong, your solution will be meaningless. Then there's the solution method. You can choose a bunch of different ways to do the numerical analysis. It's usually hidden from you, certainly in the simple model in SolidWorks, it's hidden from you, but understanding something about how the simulation works, i.e. the background math, really helps you in understanding the role of the solution method. Then there's the output, and you can do all kinds of fancy schmancy things with colored plots and everything. Mostly that is just icing on the cake. But you want to make sure that you understand enough of the output methodologies and the tools and tricks you can use to actually represent and show your model in a realistic light and really look at what the solution is telling you so that it makes some sense and you can draw some design conclusions from it. There's one more part of this that is buried to some extent and hidden from your view, and that's the basic physics. The governing equations are essential. Without knowing what you're modeling and how you're modeling it, then everything else is just sort of meaningless. And the way that that comes into it in the two finite element packages that I'm going to show you is it's not clear necessarily that you're selecting a set of governing equations, but fundamentally that's what you're doing when you're choosing an analysis method. So with that as the as kind of the plan or the general trait of an FEA analysis, I want to quickly jump into doing a really simple one with you. So here's SolidWorks. You're familiar with it. This is just in the part mode. And what I've got here is I've got a 200 millimeter long rectangular bar, and the bar is 10 centimeters, whoops, 10 centimeter or 10 millimeters in square and cross section. So this is a very simple solid part. And I know this is incredibly simple, but this is a great way to show you a simple starting point. Now, in SolidWorks, you'll see if you've made this in part mode that you should have a tab button here that is SolidWorks add-ins. And if you click that, you'll see there's a bunch of additional tools. You've probably played with some of them at this point already. One of them is simulation. Now, if this doesn't show up in your version of SolidWorks, go back to the installation for the licensing, and you can click a tool in the installation process that will add the simulation tool to your license. You have a valid license for it. So if you select that, you should be able to open up a new simulation. And you'll see once this new window titled simulation opens, you can create a new study. Now, one of the last thing I said in the overview was that the governing equations are kind of buried. Well, the place in SolidWorks where you choose what your governing equations are going to be is genuinely buried right here. That if I choose static, that essentially is saying I'm going to use some basic solid mechanics governing equations. If I was to choose any of these other like thermal or fatigue or buckling, that would actually, even though it's just clicking a button, be driving the whole model with a different set of governing equations. So for now, we're going to pick static, and that's created a new static study window. I'm just going to call that static example. And you'll see at the bottom tab here, a new window has opened up. Now I have a previous study that I've already done, but I'm going to start this one from scratch. The first thing that opens up in SolidWorks is a selection of tools here. And this first one is allowing you to choose the material. And I'm going to apply one of my favorite materials, plain carbon steel, to this model, and there it is. And then there's these other simple icons. Now, while they're not using the same language as you would in math, what these are doing are giving you options for what are called boundary conditions. I'm going to choose fixtures for my first boundary condition. And if I go up to the fixtures advisor here, I'm actually just going to fix that end. And so now I've got the top end of my bar is basically nailed to the wall or fixed in space. Now the other thing I want to do is add some external loads. I want to apply a force, and the force that I'd like to apply, I want to apply it on that face. I don't want it to be pointing upwards. I want it to be reversing in direction. I want to pull downwards. And I'm going to make this 1,000 newtons. There, simple as that. I've given it, I fixed one end, and I've applied a force at the other end. I've set the boundary conditions. If I hadn't fixed the top end, then it doesn't matter what force I would put on the bottom, it wouldn't be a static example because there's no way to satisfy the equilibrium equations. Now, the next piece here is the mesh. And if I right click on this, I can choose Create Mesh. There's some other tools here. I'm just going to pick Create Mesh. And I've got some choices. I'm going to start off with a very coarse mesh. And I can choose some mesh parameters. I can make the dimensions of my mesh bigger or smaller. I'm going to pick a very coarse mesh, 5 millimeters. And so now you can see that my model has these triangles on it. And what essentially I've done is I've divided the solid model up into tetrahedrons, essentially, that look like these triangles. And so the equations that will be solved are going to be solved for that mesh of triangles. Now, that's all there is to it. I can run this study, and it runs, and you can see that I've got some solutions. Now, even though the mesh that I created was quite coarse, you can see some features of it here, the way that the triangles that were there are still present. And we'll see when I go through more deeply how the equations are solved, why this is so. But basically, it's showing that the bar that I'm pulling tension on here is necking down at the end and getting slightly smaller, which, if you remember your strength of materials, that would be the Poisson's ratio effect, where when you pull something axially, it will tend to neck down and with the Poisson's ratio. So even though this was a coarse mesh, that's interestingly present. Now the other thing I can look at is the displacement. And this shows in the colored plot here, blue is essentially zero displacement and red is big displacement. The bottom end was being stretched, and it's moved further than the top end. So my stress, you can see, was fairly constant once you get away from the end effect of the mounting point of the bar, and everything else is pretty even, which is what you would expect. The last thing to look at is the displacement. And if we look over, should be able to look at the results advisor. And we can see that what this is telling us is that the total displacement of the model was essentially 9.51 microns. So remember that number, 9.51 microns. Is that right? Well, we're going to look at this with some other tools, but one of the things that we might want to do is change the size of the mesh and see if that number changes. But first, let's cut away and do some hand calculations and say this was a really simple model. Can we actually compare this to hand calculations and come up with a similar answer? So let's look at some basic theory that you've covered in Strength of Materials class in your second year. For axial stress, the most simple case of stress analysis that you've done, or axial strain, if we've got a long linear bar of something with a cross-sectional area A and a length L with a Young's modulus of E, that's the modulus of elasticity, and you apply a load P to either end, then the change in length, that change in length formula, PL over EA, we can apply that to the simple rectangular bar that we've drawn in SolidWorks, where A is 10 millimeters squared, and the length is 0.2 millimeters long. So we can calculate the area, 0.0001 meters squared, apply a load of 1,000 newtons, and then simply calculate delta L over EA. If we take, for steel, Young's modulus is 2.1 times 10 to the 11th pascals, then we end up with a change in length of 9.52 times 10 to the 6 meters, which is 9.52 microns. So let's compare that to what we got with substantially more effort using SolidWorks. There. So we did get a similar answer. We came up with 9.52 microns, which was pretty close to the answer that we found in the simulation. So that gives us some confidence that that answer was right. But let's do another little study here. Let's see if by changing the mesh size that we can change that number still, because ultimately the result that we calculate, whether it be through a simulation or through hand calculations, shouldn't depend on something so artificial as the size of the mesh. A standard way to prove the validity of your simulation is to change the mesh, maybe have the size of all the elements, and then run it again and see how much the number changes. So let's give that a try. And I'm going to go back to create the mesh again, but this time I'm going to go from a 5 millimeter mesh down to a 2.5 millimeter mesh. And you can see that the number of mesh points has increased dramatically. And if I run this study again, I haven't changed the boundary conditions. I haven't changed anything else about the model. I've just cut the mesh in half. And now we look again, and the displacement over here has changed a little bit, 9.511 microns, but not a large amount. We'd have to look at that number and see, is that change acceptable to us? The solution took longer time to compile, not so much, because it's a simple model, but we did get a numerical difference. The other thing we can look at is that maximum stress. Now, the color coding is irrelevant. It's just simply a feature stylized. It's the numbers that matter. And the stress in this model, you'll recall that when we looked at it before, the size of the necking down region was somewhat affected by the grid size or the size of the elements. And here too, that necking down region is smaller, but there is still this triangular characteristic of it. And so even on a smaller scale, we're still seeing the effect of that. So that was 9.51 microns. We can try this again. and renew the mesh, right click, go back to create mesh. And instead of 2.5 millimeters down here for the mesh dimension, I'm going to reduce the mesh size down to 1 millimeter. And that's a bit more realistic. Still an enormously detailed mesh, and you can see it here. Then when I try to solve this, going through the solution, you can see that the elapsed time is much longer than it was taking us before. And with a simple part, maybe you're not too worried about that. 12 seconds isn't that big a deal. You can see that once again, the features that are here in the detailed corners are smaller still because the mesh size is smaller. So what that should say to you is that perhaps these aren't real features necessarily. There is some effect of this, but what we've done is we've created artifacts in the simulation that aren't exactly represented in real life in the way that we've shown them. However, if we look at the results, the results advisor is a good tool. You can see that now instead of 9.511 microns, it's now 9.512 microns. That's a small change perhaps, but it is a difference. You can see that the maximum stress is pretty much the same as it was before. The color again isn't meaningful, but because this is such a simple body, you'll find that the stress is fairly consistent. So in this model, we could look at those values that we've constructed, where we got 9.52 microns with our hand calculation in terms of the change of length of the bar, the stretching of the bar. We got 9.511 with our coarse mesh initially, and now we've got 9.512 with a finer mesh. And we could plot those results and we could see generally a decreasing change. And with that decreasing change, we could start to look at that and say, well, what should be the right size mesh for a model like this? And that's how we're going to validate all of our simulations, is looking at variations in the boundary conditions, variations in the meshing, and looking at levels of complexity that are and are not useful. So that's enough for SolidWorks like this. I want to show you the other tool that we have at our disposal. You've seen in a simple scenario using SolidWorks to do a finite element analysis. Not a very interesting one, but still, it was a finite element analysis. If we go back to the model, and this was the original model that we created, and we do a save as of this part, and if you save this as a step, here you'll see at the bottom an STP, and I'm just going to save that on my desktop as a step. And I'm going to open up ANSYS Workbench. Now, ANSYS Workbench has a totally different interface than what you're used to in SolidWorks. The first thing that you'll see when you open this up from the default is this crazy looking bunch of options on the side. And remember when I talked earlier about the governing equations? Well, what ANSYS Workbench allows you to do is to choose the governing equations from a wide variety of scenarios. And make no mistake, these are linked very carefully to mathematical models of different types of finite elements and the solutions for those. So just to carry this through, we're going to grab this. So I index finger click there and drag static structural into this open space. Now we could have several different solution methods here that we can link together. But for the moment, we're going to start out with static structural. If you double click on engineering data, the default is structural steel. That's good. Now the structural steel tensile strength and the material properties we can look for, and we can change all of these things to whatever we want. I'm just going to leave this at the default. And if I close that, you'll see as each of these steps we go through, we get a check mark, meaning we've done them correctly. Notice that we start off with the governing equations. We've got some material properties, engineering data. The geometry is next, and then the model, the setup, the solution, and the results. Very much like I showed at the beginning of this video in the main elements of a finite element model. So if you right-click on the geometry box, you'll see that there's a bunch of options you can do: new space claim geometry or a new design modeler geometry. Space claim and design modeler are two different solid model creating tools that you can use in ANSYS, and you can use them if you choose. But the easier way is to simply import geometry from a file. The step file that we created in the previous example, we should be able to find it here as a SolidWorks STEP file. And if we just simply import that, it imports directly as a solid into ANSYS from the stored file. If we double click on model, we'll get this mechanical workbench opening up, and you'll see that it's imported in the solid model that we started with. It's created the geometry and the materials. We've already chosen structural steel as the default, so that's good. And the coordinate system is what it was in our CAD model. The only thing we have here that we haven't dealt with yet is the mesh. And we can look at the mesh. The big difference between ANSYS versus SolidWorks is how many more tools that you have at your disposal to actually edit and change and optimize the mesh, as well as to edit, change, and optimize the solution methods that you're going to use. So the power that you have at your disposal in this tool is quite a bit more than you have in SolidWorks. And if we choose mesh and generate, then you can see that we get a pretty coarse looking mesh here, but it's a mesh. Then we need to add the boundary conditions. So you'll see if you click the static structural analysis that there's some options that show up here. I'm going to start with supports. I'm going to pick a fixed support there, and I'll pick that face. And you'll see that if I click apply down here, then it's applied that to the face. And then the next thing I'll pick is a force, and I'm going to rotate it around, and I'm going to select that geometry and click apply. And I want to pick a magnitude of that force, and that's 1,000 newtons. Whoops. Better do capital N. There. And it's pulling it actually as I wanted. And so that's everything that I need. The only thing left is I'd like to make sure that I plot the deformation I'm going to pick the total deformation. I'm going to pick the equivalent stress, and that'll be sufficient for me. And then solve. And now if I look at the solution, I can look at the total deformation, and you can see that this is a similar plot to what I had in SolidWorks. If I look at the equivalent stress, you'll see that there's the equivalent stress. And the deformation, the maximum deformation that this shows is down here at the bottom. We can put a probe, we can pick the maximum deformation. And you can see that we can put that probe there and see that our maximum deformation for this model is 9.982 microns. Now, that might be larger because of different material properties, or it might be larger because of the different arrangement of elements that we've chosen. So we can go back to the mesh, and we can update the mesh, and we've got a solution. Total deformation, we haven't changed the total deformation very much. Basically, it's the same. The stress, we can plot the stress, and we can look at the stress in very much finer detail. And you can see that with this smaller mesh, similar to the SolidWorks model, the colored boxes, which are an artifact of the size of the elements that we chose, have changed. They're not triangular like they were in the model that we chose in SolidWorks, because the size and shape of the elements are different. Now, the power that we have in ANSYS is greater control over the types of elements that we've chosen. Now, in this case, I only chose a really fine dimension in one direction, and even with that, it was quite a bit of computational power to calculate these results. We were just working within one of these solution elements. As you can see, there's a whole host of other types of solving engines that you can use. This is just represented within the main workbench. So when you're designing your part, you can look at the structural analysis of it. You can look at the thermal analysis of it. You can look at acoustics, fluid flow, all of these things. You can look at independently and coupled to see how the results might impact each other. The difficulty you can get yourself into is huge, but once you know how to use it, the power to use it is similarly huge. So that's a quick tour of SolidWorks using the finite element analysis tool that you have at your disposal there. And then it's an introduction to ANSYS, which is a more powerful tool. Both of them use a similar approach in the sense that they're both finite element analysis. They both are driven by fundamentally the same math, but the solving engine that they use and the way that you have to go through the solution is quite different. And ultimately, your power in analysis of different, more complicated type systems is only limited by the tool that you're using and your ability to manipulate it. So before we move any more beyond this quick intro, well, it wasn't that quick. Before we move anywhere beyond this intro, we've got to step back and actually lift up the hood and see what's underneath these finite element analysis solution engines. So stick with me for the next video to get into the math. See you soon.